Today's talk is about the latest cosmic discoveries and the state of the Arab world. Arab astronomy. Please welcome with me Professor Nidhal Gessoum.
Assalamu alaikum, good morning, welcome everybody. Thank you very much, Omar, for the kind introduction, and thanks to you and to Stefano for doing the hard work that allowed my presence here and my trip. Very enjoyable so far, and I'm sure it's going to be until the end. I also want to thank the distinguished deans for having organized my stay and my series of lectures. I want to warn you that this is a long lecture. I'll try to skip some slides and try to shorten it as much as I can. And the reason for this being a long lecture is because these are two essentially distinct topics that have been lumped together or just added one after the other. One being the latest cosmic discoveries. What have we been finding in the cosmos that is of note that people should know about, all educated people should know about. And then what is the state of Arab astronomy, because it would be too much to talk about the state of the Arab world, so let's just try to stay on Arab astronomy. So I'll try, so forgive me if I take a little bit too long. I know people don't like long lectures and prefer interactions, and I'll be here after the talk to answer any questions for as long as you wish, and even outside. But there's some information that needs to be addressed. The first thing I want to mention is that astronomy has come a long, long way. Astronomy, I tell my students, is the oldest science. It is a science that has been practiced by all peoples from the time that from which we have any record. From every civilization, there have been contributions from all over the world, from China to the Incas. But in the last century or so, there has been a new revolution in astronomy, and that is going to space. Now, only, I wouldn't say a small fraction, but the amount of astronomy research that is performed from space is phenomenal. The reason for that is because, first of all, we made it to space in the late 1950s, and because, as you can see from this diagram on the screen, our atmosphere blocks a huge amount, a huge fraction of the electromagnetic spectrum. Most of the infrared and ultraviolet actually does not reach us on the ground. The X-ray, gamma ray, microwave, all of that does not reach us on the ground. What we get on the ground is only the visible light, the radio emissions or the radio waves, and some wavelengths from infrared and ultraviolet. So when we realize that there is so much information that comes from the cosmos that is not reaching us on the ground, then we decided, when we became able to go catch it above the atmosphere, or at least very high in the atmosphere. So this is the first thing to keep in mind, that there are now many satellites that are completely devoted to astronomy. Those satellites, they are looking outward. They don't look at the Earth. They are not there to communicate with us or to take pictures of the Earth or do remote sensing or any such thing. But we get astounding amounts of information from space, such as, for example, I will get to this in a minute, the search for exoplanets, which is perhaps the most exciting, the most active topic of astronomy today. And most of that is being done from space, as I will mention a little bit later. The entire X-ray and gamma ray domain, which you can see here, is all of this here in the electromagnetic spectrum. All of that is done from space, and we have now at least half a dozen satellites that are devoted to doing that. In fact, now we have satellites that are devoted to specific topics within the gamma ray domain or within the X-ray domain. The other sort of just brief mention here is that until about a year or a year and a half ago, we had radio dishes on the ground. Radio dishes, for some astronomical reasons, which you can ask me about later if you want, have to be very large. Essentially, they are the same dishes that you use to watch satellite TV channels, but they have to be much, much larger. And typically, they are 40 meter, 50 meter, 60 meter big. The largest one which had been in operation is still in operation in Puerto Rico. The Arecibo Observatory had a diameter of 300 meters. That in itself is already staggering. I mean, 300 meters is quite a bit, some fraction of your campus. Now, last year or a year and a half ago, China inaugurated this big this big dish, radio dish, which has a diameter of 500 meters. It has just started operating, and I'm sure there's going to be quite a bit of information. So this is astronomy today. Big instruments on the ground, in space, catching waves and radiation that is completely different from the visible light that we see. For maybe 95% of human history, all of the astronomy that we were doing with our eyes, whatever our eyes could see, whether we used instruments after we invented the telescope in the early 17th century, or we were just observing directly with our eyes. For the largest period of human history, it was all done with naked eyes. And now, as you can see, naked eye is limited to this fraction over here. All of the rest over here, which contributes to astronomy, is completely invisible to our eyes. So that's the first thing that you need to keep in mind. Now, as I mentioned a moment ago, the hottest topic, the most exciting topic of today is the search for exoplanets. Exoplanets means planets that exist outside of the solar system, exo, outside. We were for a long time convinced that there must be many, many planets around other stars, just like there are planets around the sun, which is a typical star. But until about 20 years ago, maybe 22 years ago, 23 years ago, we had not discovered any planet. And now, once we started to develop techniques, very smart and sophisticated and very subtle techniques, which I can tell you about later. Again, I don't have time to explain all the details and how that is done, but that is a fascinating new development in science and in astronomy, how we go after planets that are very far away. To just give you a glimpse of why that is a huge achievement, if you realize that all the stars that we see, and almost all the stars that we see, even with the largest telescopes, we see them always, almost always, except for very few exceptions, as tiny dots in the sky. Even when you turn a big telescope, several meters big, toward the star, and the star could be thousands of times. We now have stars that are millions and billions of times bigger than our sun, and you try to see it with a telescope, you see it as a point. Now, a typical planet, like the Earth, is 1,000,000 times smaller than a typical planet like the sun. So imagine a planet, even if it is like the sun, at tens, hundreds of light years away, orbited by a planet which is 1,000,000 times. At best, if it is a giant planet like Jupiter, it is 1,000 times smaller than that star. If the star now, even with the biggest telescope, looks like a point, imagine how the planet is going to look. We have very few cases, maybe 24 at most, out of, I will tell you in a moment, that we have, in the last 20 years or so, discovered 3,700 exoplanets. Out of these 3,700 exoplanets, there's less than 20 that we have been able to see as an image, and when we see them as an image, they are barely tiny, tiny points. So that gives you an idea of how difficult it is to detect these exoplanets. And yet, we now have a whole huge bunch. Let me show you this animation that tells you how things evolved. So this is the number of planets that we knew about, and as you can see, for a long time it was 9. Until now, 1995, we start to have planets. The planets that you see up there, every point is a planet, are big planets. Those that will appear in a moment down here are the smaller planets. And you can see it is now just, very, very fast it is filling. This is going to repeat again, this fast animation. You see, for a long time, we only have the 8 or 9 planets. In 1930, we discover Pluto, then we remove Pluto later from the list. But now you can see, now we start discovering in the early 21st century, we start discovering planets, and all of a sudden it fills up because now our techniques are sophisticated and able to discover, and now we have planets that are the size of the Earth. We have even planets that are 10 times and more than 10 times smaller than the size of the Earth. Why is this exciting? Because in the end, we are trying to find other Earths. Why are we trying to find other Earths? Because only planets that are more or less similar to the Earth could possibly host life. So if I am just being an astronomer, I'm interested in all kinds of planets, I'm interested in all kinds of stars, I'm interested in all kinds of black holes, galaxies, nebulae, you name it. But as a scientist or even as a human being, the biggest question on my mind is there life elsewhere? And to find other life elsewhere, we need to find planets or moons. Now there is another whole branch of searching for exomoons. That's even harder, but we are going after exomoons, believe it or not. But let's at least focus on the exoplanets, and we ask ourselves, what kind of exoplanets could possibly host life? We know that the giant planets like Jupiter and Saturn could not normally, if we define life as we know it, more or less. There has been all kinds of science fiction that has imagined all kinds of life inside Jupiter, etc. But let's keep it to the normal life based on cells and DNA and normal metabolism, etc., etc. That will require an object that can have liquid water, preferably, not absolutely necessary, but very much preferable. Preferably having an atmosphere, a decent atmosphere. If you have too big a planet, then the atmosphere is going to be so huge, it will crush anything. So that's no good. If you have too small a planet, then its gravity is too weak. It will not attract gas. It will not have much of an atmosphere. So for example, remember that Mars, or you probably know, Mars has an atmosphere of less than 1% of the atmosphere that Earth has. Jupiter has an atmosphere that is thousands of times stronger, so that's too much. So we want medium-sized planets like the Earth. There's a reason why life exists on Earth, is because Earth is perfect with all its physical, biological, astronomical, chemical conditions. And so we try to find other Earths. So that, in a nutshell, why. And so we have been beginning to find planets that are sort of the size of the Earth, and preferably, if we can, find these other Earths surrounding stars that are similar to the Sun. Why are we, again, looking for something that resembles what we have? Because it so happens that the Sun is sort of the perfect star, because it is medium-sized, it emits steady radiation, it is not too volatile, it doesn't have too many huge flares, it lasts a long time, it allows for life to develop and evolve over billions of years. So we think that this is the perfect condition. We might very well be surprised later and find a star that is very different and the planet quite different, and then all of a sudden we find some kind of life. That is possible, but probabilistically all the scientists agree that something like an Earth or Earth-like planet surrounding or orbiting a star that resembles to some extent the Sun is our best hope. And just about a year ago, we found a very interesting system, a star that has 7 planets, all of them more or less similar to the Earth. Like, whoa, this is fantastic. Even better than that, you probably know, because this was probably huge news here in Morocco, one of the participating teams was the Akhawayn Observatory near Marrakesh. This was huge news. It was front page on all the newspapers, CNN, New York Times, you name it, Nature, of course, Nature paper. These people became celebrities because they had found 7 Earths around one star. Not only that, but 3 out of the 7 orbit the star in what we call the habitable zone. This green zone here is the zone where the temperature is somewhere between below 0 and a few tens of degrees. Why do we want a region where the temperature is somewhere above 0? Because that's where water, if it exists, is going to be liquid. Now you say, yeah, but are you sure there's going to be water over there? Water, H2O, is a very easy molecule to form in the entire cosmos. Almost everywhere we have looked, we have found H2O in one form or another. Water vapor, ice, and in some places, liquid water. So if the temperature is adequate, we are pretty sure there will be some water, and then it is just a matter of how much water, is it liquid, is there an atmosphere around these planets, and then could life have developed? Now, there was one negative or one disadvantage. Nothing is perfect in science or even in astronomy. This star actually is a very small star. You say, yes, so? So these planets, first of all, the star being small is not very stable. It is very erratic. It has all kinds of flares, and it keeps bombarding its planets with all kinds of radiation. So that's no good. If any life developed here, it has probably been irradiated 1,000,000 times. So that's not very promising. Secondly, because this is small, it has a weak gravity. These planets have to be close, much, much closer than our planets in our solar system. You say, yeah, let it be. Let them be close. Get some warmth. No, if they get close, then they get too much tidal effect. So then anything that is happening on those planets is just going up and down and a bit too crazy. So this is not the most ideal situation, even though I forgot to mention, this whole system, this whole miniature solar system is very near by astronomical standards, only 40 light years away. 40 light years is just next door. Of course, people ask me on social media, so how long would it take to get there? Can we go? And I tell them, well, if you have 100,000 years to spare, hop on the next spacecraft and go. So the fastest spacecrafts today, with today's technology, would take something like 100,000 years to get there, perhaps even 1,000,000 years. But hey, we are scientists. We don't get deterred too easily. We continue. So this is the resemblance of these 7 planets to the 4 terrestrial planets. As I said, we are not interested, 4 terrestrial planets of our solar system. We are not interested in the gaseous planets, Jupiter, Saturn, Uranus, and Neptune. Those are useless for this regard. So we want to compare these to the planets that we have in the solar system. The 2 best hopes, of course, in the solar system are not hopes. Earth, we know for sure there's plenty of life. Huh? We are alive, right? And Mars, maybe. I personally am not too optimistic about Mars hosting life, but it is a very, very possible place, location. Now, I usually put these images not just to make it a beautiful talk, but to warn people to realize that whenever you see these images, and you see them all the time when there are discoveries of exoplanets, you will see them on TV, you will see them in the news, you will see them everywhere. I want to warn you that we have no images of any such places ever, ever. This is a very good drawing, a good painting, somebody imagined from the information we give them. So we say these planets are this kind, they are at this distance from their stars, etc. Try to imagine how it would look like, and then they paint this, and then we show them on PowerPoint, okay? So this is the only reason why we show these things, not because anybody has taken ever any image of any exoplanet. This would have meant that somebody went to the exoplanet, landed there, and took the picture, okay? So there are no images of any exoplanets ever, ever, okay? At best, as I said, and I could show you some images of the couple dozen planets that we have actually imaged, meaning taken a picture with a telescope and the CCD camera and something sophisticated, and you can barely see a point, and it is a very blurry pixel. 1 pixel in an entire image. That's the best we can do now. The closest exoplanet to Earth is actually a planet that orbits the closest star to Earth. We will not find closer than this. Not possible, because this is the closest star to us. Proxima Centauri, which, by the way, is part of a triple system, triple star system. These are 3 stars together like this. Around this small one, again, another small red planet, star, no good, not very good. We found a planet orbiting around it like this, so this is the closest you could have to the solar system, only about 4 light years away. Only. I'll skip over all of this. This is how again, somebody imagined this planet labeled Proxima b to be of the same size and shape and maybe even surface as the Earth, but again, nobody has seen anything like this, okay? I'll skip over all this. This is going to restart now. You remember this animation earlier, which was already full with 3,700 planets. This is imagining or predicting on the basis of current research where we're going to be in about 10, 15 years. And you can see, watch this number, for example, here. This number is the total number of planets year after year. You see this? 100,000 now. So within 15 years, we will have not 3,000, we will have 120,000 planets elsewhere. Among these 120,000 planets, there's going to be Earth-like planets by the thousands, And there's going to be Mars-like planets by the hundreds, perhaps the thousands. Exciting times to come. Every year you're going to hear new discoveries and new interesting situations. Now, as I said, the ultimate goal is to search for life. How are you going to search for life on a planet that you can barely see as a point in your biggest telescope, right? That is the amazing feat that scientists are able to do today. So what do? We look for signatures of gases in the light that we receive from those planets. You say, so you're receiving light from the planet? Yes. We are looking at the star, actually. All this research, most of it is just focusing on the star. When we see the star doing something which I don't have time to explain to you, then we conclude, we infer that there's a planet. However, when the planet is orbiting like this, and when it goes behind and starts to send its light, reflected, of course, from the star, reflects on the planet, goes back, if now this light goes through the atmosphere and reaches us, then we can analyze the light that has reached us and see whatever signature there is in the light that we have received, which tells us if there is an atmosphere and what it is made of. Very, very fascinating, complicated, sophisticated techniques, but we can analyze the light and figure out if there are some interesting gases. What are these interesting gases? The interesting gases are those that are associated with life. For example, oxygen. For example, one of the most common gases would be CO2. CO2 does not mean that there is life at all. CO2 is associated with geological activity, release from the planet's surface, etc., but it doesn't mean at all. Now, if you find oxygen, it means something is absorbing the CO2 and releasing the oxygen, photosynthesis. So that, at the minimum, it means there's some vegetation, there's some plants. Now, if you start finding ozone, you start finding methane, you start finding, even if you find, for example, just water vapor, signature of H2O in the light that you are receiving, then that does not mean there is life, but it means there is water. And possibly, if we know the conditions of that planet, as I said, it is in the habitable zone, etc., then it's probable that the water is liquid. And if the water is liquid, then everybody will be focusing on that planet, because there's a high probability, not high probability, but a very good possibility, let's say, that there could be at least some primitive life, at least. So this is how we would do. So if let's say there is some alien civilization that is looking at our solar system, and it receives the light that is which is sunlight, being reflected from these planets, this is Venus, this is Earth, and this is Mars. So as you can see from all three, there's CO2 signature over here in the spectrum of the light that is being received. So this doesn't mean anything. Now, for Earth, say, whoa, wait a minute, there's H2O, here there isn't, and here there isn't. So this is very promising, and then you see ozone, and you say, wait, hold it. Now, very, very interesting. Now, something really complex is going on because I can see ozone. And then you continue, and you start to find real oxygen, O2, and then you start to find methane, and so on and so forth. So now, second topic of interest these days is Mars. Again, because we are looking for life on Mars. Mars is one of the interesting places in the solar system where there could possibly still be life, or at least life may have appeared and evolved, perhaps disappeared in the past, in the long past. We know for sure today, again, I don't have time to explain all the details, we know for sure that Mars had lots and lots of liquid water in the past. And then that got evaporated and lost. So during that time, during those millions and millions, perhaps tens of millions of years, when Mars had seas and perhaps oceans of water, could it have developed life, at least primitive life, which could have gone underground and maybe survived or at least left some signature? This is what we are looking for because we want to understand how easy does life appear on any planet. If we find life on Mars, then we say, whoa, life appears very easily. Look, Mars only had water for like 20 million years, and immediately it had life, and immediately, and it survived and stayed there underground, etc. There are, in my view, other more interesting places in the solar system, including my favorite place, Europa, one of the moons of Jupiter. But Europa is too far, although NASA is still working on a plan for a mission to go to land on Europa and dig and try to see if there's anything there. But the closest one and the easiest one to get to is Mars. So we'll be going to Mars. We've been going to Mars, and Elon Musk has promised to take people to Mars within 5 years or 6 years or so. Let's see. Anyway, so this is Mars. Mars, we have sent all kinds of spacecrafts that have landed. Some of them have crashed. Some of them have been lost. Mars has been difficult to tame, but we have made it to Mars many times. Right now, we have big vehicles that are roaming on Mars and making all kinds of measurements and detections. One of the exciting, it was very exciting until it became de-exciting, discoveries of maybe 3 years ago or so was, there were some images taken by an orbiter. So sometimes we send spacecrafts that go and land on Mars, and sometimes we just let them orbit and just take all kinds of images and measurements and send them back to Earth. It is easier to do orbiters than to do landers, much easier. We have had recently even some attempts to land and then crash. Then the whole thing is lost. People have worked for 10 years and then it's just gone. So orbiters are much easier. So one of the orbiters took images and saw these kinds of streaks on at least one hill. This in itself was not so spectacular because we had seen things like this, although not so clear and amazing, but we had seen streaks on hills and mountains before. What was so exciting about this was that when the same place was imaged, and I think this is an animation or should be an animation. Let me see. No, this one is the animation. So it shows you how, and you can see the changes. You can see the changes. This is just a few weeks to a few months apart. You can see the changes, which means that these streaks are appearing and disappearing as we speak, meaning within a few weeks and within a few months. This is not something that happened 10 million years ago and just left some traces. This is something happening right now. So people concluded that this must be water seeping from inside of the hill to the outside, downhill, and leaving some traces like this. People said, wait a minute, how could there be water flowing, which would mean liquid, when the average temperature on Mars is something like minus 30 degrees? How can you have liquid water? Oh, then the chemist said, easy. Hey, we can solve this for you. Just put lots of salts, all kinds of salts, and then the melting temperature drops, and you can have liquid salted water flowing at minus 20 or minus 10. Temperature on Mars does go above zero for a few hours during summertime on Mars. So in the day, in the best summer, the best hours of the day in summer, in the best places, you can get to maybe plus 10, okay? So that's not unheard of. Which explains why there was liquid water in the past, etc., etc. Now, the reason why I said we got de-excited, because people redid the analysis and observed and said, it is not liquid water, it is not salted water, these are most likely sands flowing, if you like, downhill without any liquid of any kind. So this is interesting that there is some activity from the hill itself, but does not indicate the presence of water. We know that there was water in the past, and we know that there is water at least in the poles in icy form, and we are pretty sure that there is water underground. But no liquid water has been found on Mars so far. Nothing. No liquid, which is the key idea. Now, this is one of the nice robots, 6-wheeled robot called Curiosity. Curiosity celebrated its 5th year on Mars in August 2017. All kinds of achievements, including, for example, in September 2017, the detection of boron. Boron is an interesting chemical element because it is very often associated with living organisms. And so we have not found any living organisms. We have not found even liquid water. But we are finding some elements, some chemical elements, and some ingredients that are usually or often associated with life. This doesn't mean there is life, but it is encouraging. The third most spectacular, historic, cosmic, astronomical, cosmological development of the last 2-3 years is the detection of gravitational waves. What are these gravitational waves? Gravitational waves are a completely different wave from the electromagnetic waves. Everything we have discovered in the cosmos since humans started to look upward, and this means tens of thousands of years, has been using either visible light or invisible light, all of it electromagnetic, until 2.5 years ago. 2.5 years ago, a completely different type of wave was for the first time detected. Now, this had been predicted by Einstein in his 1915-16 general theory of general relativity, which is a big theory of gravity, a different gravity than what Newton had told us. He had predicted it, but Einstein himself said, I don't think these kinds of waves will ever be discovered. He didn't say will be discovered in my lifetime. He said, I don't think they will ever be discovered because they are so weak, it is just unimaginable for me that anybody will be able to do it. Well, as we say never. So within a century, it is, I mean, if I could give a whole talk on this and just tell you how amazing this feat is, the discovery. Let me play, so what was discovered? What was discovered is when you have two black holes, two mid-sized black holes. These are not small black holes, by the way. These are big, chunky black holes. And they go around each other if they happen to be in binary, I call them the married ones, okay? They go like this. And then if they attract each other too much, and after a while they merge. When they merge, part of the mass and energy that they carried is released in the form of gravitational wave. Those gravitational waves will spread throughout the cosmos. And some of them will reach us. And if we have the right detection apparatus, then we can record that. And that's what people did. So let me just play this animation of how this goes. So both of these are black holes. Both of these are black holes. You can see the black holes here. This is supposed to represent the gravitational wells. This is just telling you how strong the gravity is in the neighborhood or in the space. This is technically space-time, but let's just say space, around the black hole. And now you're going to see that they're going to get closer and closer and closer until they merge. So this is what happened. This is what happened, I was going to say 2 years ago. This is what happened 1.3 billion years ago. And it took about 1.3 billion years for this information to reach us, even though it was traveling at the speed of light. Okay, so this is far, far. So this is just freezing, just so you see. Now we have one merged black hole. Now you can see just around, you can see the gravitational waves forming now and spreading over here. This is what we are after now. Then this starts to spread, you can see all of these. And then 1.3 billion light years away over there, there's something called Earth. And some people put some devices. Again, I don't have time to explain. These are very big lasers, laser beams that are 4 kilometers long each, believe it or not. And then they send them and they keep reflecting back and forth like this in perpendicular directions. You can see them there. And then we do something to the two laser beams. And if they show some kind of signal, then we say, whoa, we know what happened. Very, very smart, very, very, it's an amazing thing. Again, I don't have time to show all of this. And from that detection, we now have about 5 detections of this kind. From that first detection, it was so historic, it was so incredible. As I said, Einstein would not have believed that anybody would be able to do that. And because it opens a completely different window, instead of being just limited to the electromagnetic spectrum, we now have a completely different spectrum to explore with all kinds of phenomena. Nobel Prize was given to the 3 people who are most associated with the developments that led to this discovery. So the 2017 Nobel Prize in Physics was given for this. If that was not enough, then last August there was another even more spectacular discovery of the same kind. Now, let me see. I'll play this while I explain what this is. So now you say, so you're showing us the same thing again? No, not exactly the same. These now are 2 neutron stars. Neutron stars are a lot more interesting than black holes, if you can believe that. I know everybody loves black holes. Neutron stars are a lot more interesting. See what happens here? What happened? What's the difference between this and the previous one? Anybody? What happened? Did you see? Should I replay it? What happened? You didn't see? An explosion, thank you very much. An explosion, very simple. Here you had a big explosion. In the previous one, there was no explosion. There was a merger, and then some invisible waves traveled out. And because we were smart to construct some interesting detection devices, we were able to detect the waves. Here, you don't have to be smart and do all kinds of devices. You can just put your telescope out and detect this. Well, I'm saying, I'm simplifying, of course, not just get out your telescope, here's your discovery. Although, believe it or not, this event was monitored by over 40 observatories around the world. Observatories, because this is visible light. It reaches the Earth. You don't have to be in space. But, of course, people said, oh, we have this opportunity, again, even more historic, and everybody who had any instrument in space or on Earth of any type, radio, infrared, visible light, X-ray, gamma ray, turn it toward that point and measure. And indeed, this event and this phenomenon was measured by every instrument of electromagnetic or gravitational wave. This is an astounding discovery, an absolutely astounding discovery, a new direction in astrophysical research. Again, I don't have time to show all of this. This is the optical detection. There were some other detections, etc. Let me go a bit faster now, since I want to get to the second part, which is the state of Arab astronomy. There were some other interesting discoveries last year, including discovery of a black hole. I said everybody loves black hole. Me too. So there was this black hole that has the mass of 100,000 times the mass of the sun. So you say, oh, is that impressive? Well, yes and no. It's not the largest. In fact, in our galaxy, we have at the center of the galaxy one that is 45 times bigger than this. It's like, yeah, so why are you so excited about this? And in fact, in other galaxies, we have ones that are even 100 times bigger than the monster that we have in the center of our galaxy. So what's so spectacular about this? Because until now, we had the so-called hypermassive, huge black holes, which you find only in the centers of galaxies. And then we had the moderate-sized black holes of a few times to maybe a few tens of solar masses of the sun. We never had anything in between. So now we're finding something. Again, I always tell people when I give lectures like this, look, in science, nothing is discovered until it is confirmed, until we confirm, and it has to be independent confirmation. This is part of the practice of science. We do not start, claiming discoveries just like that. But these are, as I said, important developments in astrophysics as we speak. For all we know, maybe next month somebody will look back at this and say, hey, excuse me, that's not a black hole, okay? So then we say, scratch that, sorry, go back. But that is part of science. We correct ourselves. We continue. But somebody could look and say, yes, I have found some more evidence that this is a black hole. And we say, great, okay. And we continue. Conclusions, there are new avenues have opened up. Small exoplanets, a lot more interesting, search for life, exploration and possibly colonization of Mars, if we follow Elon Musk. Gravitational waves, intermediate mass black holes, and will thrive, all of this will thrive in the years to come. So now I think if my watch is correct, I have about 15, 20 minutes left. So let me talk a little bit about the state of Arab astronomy. We all know that we had a long, glorious past in astronomy. Yes? This is not just to be nostalgic and apologetic and we were great, okay? But this is to contrast the state of astronomy 1,000 years ago, 500 years ago, with the state of astronomy in the Arab world today. Early in the 9th century, Al-Ma'mun ordered the construction of 2 observatories, perhaps possibly the earliest observatories in the history of humanity, were made at the very beginning of the Abbasid period, which meant that people were immediately interested in science and astronomy. This is another argument that whenever people tell me, so what's the use of this? Why are you wasting time and money and all of this? You know, the utilitarian approach. And I say, 1,000 years ago, more than 1,000 years ago, your ancestors, the moment they started even building a civilization, went after astronomy. Astronomy was one of the first sciences to develop in the Islamic civilization, and very possibly the last one to disappear. Anyway, so observatories, main reasons for building these new institutions of research: to check and reconcile data found in old Greek and Indian tables, use for Islamic religious practices, astrology for the rulers. Let's skip over this. This is the old past great observatories follow up. So there were the 2 first observatories that Al-Ma'mun built outside of Baghdad, the Shammasiyya, and outside of Damascus, Dimashq, the Jabal Qasyun. But then later, much bigger and much more sophisticated observatories were built. Maragha, which is now in western northwest Iran, Samarkand in Uzbekistan, Istanbul, many, many places, large observatories. And then I haven't even mentioned the ones in the Indian subcontinent, in Jaipur, in Delhi, which I have visited myself. It's just absolutely amazing, and everywhere. So this is a reconstruction. This is sort of a painting of showing how huge sextants on the ground. This is the so-called Fakhri sextant. Anyway, contributions and legacies. There's at least 300 stars in the sky that carry Arabic names. Some of the most famous stars, some of the largest and brightest stars, until today carry Arabic names, including Al-Ta'ir, Deneb, Vega. Vega is Nisr al-Waqi'. People are astounded to hear that Vega is an Arab name. Al-Dabaran, Al-Ghul, Mizar, Rijl, etc., etc. Lunar craters, there's, if I recall, I think 15 or so craters on the moon that the International Astronomical Union named after illustrious Arab Muslim astronomers to today, including Al-Battani, Al-Bitruji. Al-Bitruji who is from Morocco and Al-Andalus, Abdurrahman al-Sufi, Al-Khawarizmi, of course, and so on. Even women, of course, even women. I think I have a picture here. Fatima al-Majritiya, that's her name. She's not the only one. There's a number of women who participated in astronomy 1,000 years ago. 1,000 years ago. Fatima of Madrid. This is by the way, this is just to tell you, I tell people 99.9% of Arabs, including educated Arabs, have never heard of Fatima of Madrid, Fatima al-Majritiya. And yet, the International Astronomical Union in 2009, when it was the year of astronomy, 2009 was the year of astronomy, UNESCO declared it the year of astronomy to celebrate 400 years for the invention of the telescope, which I rank, and I'm not exaggerating, not because I'm an astrophysicist, okay? But I rank alongside the computer as the 2 most important inventions of all time. And I could explain why. Really? The telescope? What good is the telescope? Nobody uses a telescope. Telescope is one of the most important inventions of all time. Anyway, when the UNESCO was celebrating 400 years of the invention of the telescope, it declared the year 2009 the year of astronomy. It issued a calendar, 12 months. One of the months, I don't remember which month, every month was dedicated to one important figure in the history of astronomy. They selected Fatima of Madrid to be one of the 12. So just to give you an idea, I'm not implying that she made huge, astounding discoveries. I am implying that women did play a role. By the way, because her father, Maslam al-Majriti, also very, very famous astronomer from the Andalus, Maslama, contributed important tables, important observations, etc. And she was helping, and she was making observations and constructing tables and so on and so forth. That was then, this is now. So what is now? The Istanbul Observatory was destroyed in 1580. No astronomy was conducted in the Arab Muslim world until late 19th century. So there's like a 300-year hiatus where people forgot about astronomy after having done astronomy for 600 years at least. And then for 300 years, like, we don't want to hear about astronomy, we don't want to do astronomy. The first observatory that was built in the modern Arab world was the Lee Astrophysical Observatory in Beirut, built by the American, what was to become the American University of Beirut, which at the time was a missionary school. And so they decided that we're going to build an observatory, and they built the observatory the first time the Arab world had an observatory equipped with a telescope, the first time that the telescope was being used in the modern Arab world, in Beirut. It was closed later in 1980. It functioned for a while up and down. It was a small a small telescope. I visited the observatory. It's closed, and it's a nice little bit. I think I have a picture of it, yeah. So this is a picture of the observatory in essentially inside the American University of Beirut, if you go to Beirut. In Algiers, the same. The French built an observatory, still exists today, in 1891. And for about 20 years, it contributed a lot to what was an international astrophotographic catalog project. And after that, it sort of became not very productive and not very active. This is the observatory on the hills or mountains on the outskirts of Algiers. This is the Helwan Observatory near Cairo, built in the early 1900s. Egypt later made advances or additional steps to do some astronomy, so it joined the International Astronomical Union in 1925. A Department of Astronomy was established at Cairo University in 1937. So this is the Helwan Observatory. This is King Farouk doing that. And then the only large observatory to have ever been built in the entire Arab world was built in, I think, 1962. This is the Quttamiyya Observatory outside of Cairo in the desert. A large, very large. At the time, it was very large, almost 2 meters big. But after that, it started to essentially not disintegrate, but not become very active, very productive. It wasn't well maintained, etc. And so today, if you look at this map, this is the map of the world where every dot here shows an observatory. And what you notice is that there are very few, if any, points in the entire Arab world region. If you haven't seen that very clearly, here's a close-up. What is remarkable in this map is that the Arab world is where you have lots and lots and lots of clear nights. For astronomers, whenever an astronomer asks about an observatory, the first thing he or she asks is, how many clear nights do you have? So we can do observations. If you are cloudy all the time, then that's not a good observatory. And it happens here that we have a region where we typically have 200 to 300 nights, clear nights a year, no observatories. And then in Europe, where they have a few tens of clear nights a year, they have hundreds of observatories. So this is really a big paradox, a big paradox. I'll come back to this a little bit later. So what is the situation today in terms of observatories? So here's the almost entire list. In Algeria, there is an 80-centimeter telescope, little research presently conducted with it. There's a new one being built, not yet operational, won't be operational for a number of years. In Egypt, as I said, there's one big telescope, which essentially is not doing almost anything now. And there is one that is 76 centimeter. For you to understand this table and the following couple of slides, one thing you need to realize or to be told is that a world-class observatory, a real research observatory, has to have a telescope of a diameter of roughly 1 meter. So anything below 1 meter is like, yeah, come on. You really want us to do research with that? You can, of course, and now there's all kinds of techniques. We have, image processing, and we have all kinds of things that we can do with even smaller telescopes. But if you really want to do research that is competitive with the rest of the world, you need something like 1 meter. The largest that we have here on Earth is about 10 meters. And there are 3 observatories that are being built right now that will be operational in a few years that are 30 meters big. 30 meters big. In the entire Arab world, as you will see in the table, there is only one that is more than 1 meter. It is more than 50 years old and is essentially not operational. Everything else is very small. You can see the 40 centimeter, 35 centimeters. This is really not right. 50 centimeter, 35 centimeter. Even the Moroccan one, and I'm not here just because, I'm not saying this just because I am in Morocco. The one really active observatory in the entire Arab world is the one at Akhawayn. Seriously. And even though it has small telescopes because the money is not available, because the budget is very limited. So they only have 50 centimeter telescopes. And yet they are doing superb work with the limited resources that they have. The other one that is now up and coming is the one in Lebanon, and you can see that in Lebanon they have even less resources, 35 centimeter, 40 centimeter. For the Arab world to be functioning with 40 centimeter, 50 centimeter telescopes is a shame, is really a shame. Although I really salute my colleagues who are doing heroic work with these limited resources. So what is the situation of Arab research in astronomy? I published a paper in Nature, not a paper, it's a commentary article, 4-page article in Nature in June 2013, if you want to go back and check all of that. So I wanted to look at, okay, so what is the research productivity? How many papers are being produced in astronomy in different countries, et cetera, et cetera. Here's what, I mean, this does not require much explaining, but this is total Arab countries. This is Israel, this is Turkey, this is Iran, this is South Africa. South Africa. South Africa has the largest observatory and telescope of the entire southern hemisphere. South Africa. South Africa has 6 times less population than the Arab world. South Africa has a GDP less than the GDP of Egypt. It has a GDP 6 times less than the GDP of Saudi Arabia. 6 times less. Here's Saudi Arabia's production of astronomy papers. Here's South Africa. That's all you need to know. In terms of astronomy education, there are very few astronomy degree programs at the BSc, MSc, PhD levels in the entire Arab world. Very few high-standard astronomy conferences, few proceedings, if ever, very little collaboration between universities, intra-Arab world or with the outside world. So to conclude, governments, funding agencies, science organizations, and universities of the Arab world must take a serious look at the state of astronomy and make strategic decisions to develop it. What do I mean by strategic decisions? Here are the proposed steps. I wrote all this in my article in Nature, and I keep repeating it. We need to start building observatories with at least 1 to 2 meter telescopes. This is not very expensive. It costs altogether, with the infrastructure, with the buildings and the roads, etc., something like $10 million. $10 million. For the Arab world not to be, for any Arab country not to be able to afford $10 million for a state-of-the-art facility for astronomical research is unacceptable. Establish astronomy programs at main universities, at least the main universities. And we keep talking about rankings and all that. We don't have a single university that offers an advanced degree in astrophysics. We need to fund graduate students to pursue doctoral astrophysics programs at international institutions. A few of these steps, to be honest, are being taken, really. A few of these. So we have a number of students who are now doing masters and PhD elsewhere in astronomy, from some countries at least. Support collaborations among Arab astronomers, short or long visits, and with colleagues worldwide. This is also being done to some extent. There is some funding, a little bit of funding that is beginning to be available to allow people to visit each other, to spend time, to collaborate within and between Arab universities. This should be done everywhere. But this is what we need to do if we want astronomy to go back to the glorious past, or at least some shadow of the glorious past that it used to have. I'll stop here. Thank you very much.